Welcome to the second lecture by Professor Johannes Schmidt-Hieber. Since I've already introduced him before, so without further ado, let's hear from him.
Okay, so thank you. First, I want to mention that the slides, I will always put them on my web page, so you should copy the link and then you find the slides in case you're interested. And the second thing is a small disclaimer. So starting with this lecture will be a bit more mathematical. So last time was a sort of an overview and an introduction, and today we will dive into the theory, and we will mainly do the theory from the 90s. I think this is very important because it lays the foundation for the deep learning, and then starting with next week we will come to the deep networks, and today it will be mainly about shallow networks. Okay, so again, what is a shallow network? And I just maybe put it on the board so you can always see that, because everything is related to that. So those are just functions which are linear combinations of these units, and we have some interesting parameters here. The m is the number of hidden the number of units in the hidden layer. Those are the parameters that we fix, and this is the activation function that we pick before we do the learning. And so what people then were studying is, yeah, so how large is this function space? Which functions can you generate with functions of by writing them in this form? And then you can go on, and once you have figured that out, you can try to get something on rates of convergence, and these rates of convergence are always in terms of the number of parameters, which is essentially the number of units m, right? So you want to see how fast can you converge, for instance, to a smooth function if you make the m large. And if you like an exercise, so a function that is not so easy to approximate is if you just take two inputs and you want to multiply them. Okay, so you just multiply two numbers, and you can wonder now, can I do multiplication? Can I somehow approximate it with functions of this form? And then if you think about this, you see that those are functions which are somehow, this is a linear function and the x. So here you can build something linear, and then you have this possibility with the nonlinearity to do something. But it seems to be very far from multiplying numbers, right? So you can wonder now, for instance, is this function, can that be well approximated by a shallow network? Okay, so in total we have so those are vectors, d-dimensional vectors, and then we have here real numbers. So in total we have d plus 2 parameters in each of these terms, and then m times d plus 2 real parameters that we can choose. Moreover, you can see that these function spaces are nested. So if I make the m larger and make it to m prime, say, then we get additional terms here, and that just increases the function space. And the thing people have been starting with, it's a purely approximation theoretic idea, is to answer the question whether it's true that any continuous function on, say, 0, 1 to the d can be approximated with respect to the uniform norm by a network if we make the m large enough. Okay, so that means essentially for any continuous function and any epsilon, we can find an m such that there's a shallow network that approximates this function f up to uniform error of order epsilon. And now you can wonder, is that true or not? The thing is, it depends, and it depends on the activation function whether this is true or not. first of all, what you should see is the one-dimensional case is much easier. Okay, so if you think about the cellular networks in one dimension, then this becomes just a, right? This is then just a number as well, and then we just somehow have these sigmas here, and if you take, for instance, sigma to be the value function, the maximum of x and 0, right? So you see that with in the one dimensions, you just get piecewise constant functions, piecewise linear functions. And so all what you have to study is somehow whether you can, with piecewise linear functions, whether you can approximate any continuous function, which is obviously true. So this is somehow the one-dimensional case is much easier. In 2 dimensions or higher dimensions, it's much harder, and that reflects here in, for instance, that you can, if you have 2 inputs, that you can do many things like multiplication or so, which are not so easy to approximate with the structure of this form. And so in the early 90s, until the mid-90s maybe, there have been many different proof strategies to prove this universal approximation theorem. And they use different ideas, mainly based on Fourier transform, on the Radon transform, and also on the Hahn-Banach theorem. And these different proof techniques, they tell us a bit about how these cellular network approximate functions, and therefore I want to discuss several of these proof techniques. The only one that I don't discuss is the Hahn-Banach theorem, because it's a completely abstract proof, and the other ones are more or less constructive, and therefore I want to discuss them a bit.
So sorry.
Yeah.
When you say that the product of x1 and x2 is difficult to approximate,
Yeah.
that you mean like the activation function can be chosen from a small set of the functions, right? Or the activation function can be anything?
No, well, I just give you this as a problem to think about. So consider this function, and now I give you the task, approximate this function by a function of this type, where m is, say, fixed, and so how do you do that? How do you do this
So
approximation?
Sigma can be anything, right?
Let's say sigma is the value activation function, okay? But even then, if you're in 2 dimensions, it's not so easy to approximate multiplication with the network, because it's a inside you have something linear, okay? So it's just a linear combination of x1 and x2 here,
Okay.
and the only nonlinearity comes through the sigma in here, yeah. So you can try it maybe as a, yeah.
But in the universal approximation theorem, sigma can be anything. So even proving that for
Oh, no.
sigma.
Okay, good point. So the universal approximation theorem is for fixed sigma. So some of the sigmas, for a large class of sigmas, this is true, but then there are also some sigmas for which it's not true. I will come to that.
So the theorem says that they exist.
There's no theorem yet. It's just a statement. So that's the definition. So we say the universal approximation property holds for cellular networks with activation function sigma if this is true, and then the theorem will come later, and that will give conditions on the sigma. Yeah, very good point. Okay. Yeah. Okay. So, and so how do these proofs work? Many of the proofs that exist, they split it in 2 parts. And in the first part, they somehow do the one-dimensional case, which I said is quite easy with the activation functions. And if you have solved the one-dimensional case, if you have proven the universal approximation in 1 dimensions, what you can do then is somehow you can afterwards just wonder whether the universal approximation holds if you take, instead of the sigmas here, you take arbitrary continuous functions gj. Okay, so because then if you have that in 1 dimension, you can somehow replace the sigma by any gj that you have. Okay, so that means somehow if you have the universal approximation property in 1 dimensions, afterwards you just have to check the universal approximation property of rich functions, and that is a much larger class, and you can do much more things with rich functions. And that's the common technique to establish the universal approximation property. Yeah, so there's also in non-parametric statistics which functions of this form, they're also sometimes considered as a function class. And then there's an algorithm called projection pursuit to fit a function of this form to data. And all what it shows, essentially, this argument shows that with these shallow networks, you can essentially also do what you could do with projection pursuit. It's quite closely related to that. Another thing is, so what I mentioned, that the universal approximation theorem does not hold for all activation functions, and the ones where it doesn't hold, and where you can easily see that it doesn't hold, is if you have an activation function which is a polynomial. So suppose you take here x squared, okay? So or sigma of y is equal to y squared. So what you get out here is, since all the you get only polynomials of degree 2 here, and as large as you make m, it doesn't change anything. You will only have polynomials of order 2, and you know with polynomials of order 2, you're not able to approximate highly oscillating functions. Okay, so therefore, if you have polynomial activation function, the universal approximation theorem does not hold, and the space is much smaller actually in this case. And this is something I will do starting with next week. If you add additional layers, then also with a polynomial activation function, because by stacking layers, hidden layers on top of each other, you can then also generate higher order polynomials. And then somehow, if you make the number of hidden layers tend to infinity, then you also can get that. But if you just look at shallow networks, then these polynomial activation functions are not rich enough in order to generate the full space of continuous functions. Sorry, I'm going the other way. Yeah. And so if we follow the strategy and we first do the universal approximation property in one dimension, then the result here is that the first result is that if the activation function is infinitely often differentiable, then you can show that the universal approximation property holds in one dimension. Okay, and that allows you then to reduce that to the problem of approximation by rich functions. And so here I have, so every good math talk has a proof, and my talk today even has 2 proofs, and this is the first one. It's quite easy to describe the main steps in the proofs at least. So here, what you do is you first define the first order difference, and once you have done that, you can iteratively define the kth order differences, where you should see that normally you should divide by x times h, and here you just divide by h. And that is the reason that, well, if you write it in this form, then you see that the kth order difference divided by x to the k, which you haven't included in here, minus the kth derivative at the point t, that converges to 0 if you make this the discretization small. Okay, so that's the first step. Okay, and if now the assumption if a sigma is not a polynomial, which we excluded, right? We know for polynomial it's not true. Then you can find for each integer k, you can find a number where the kth derivative does not vanish. Okay, and we call that the sigma is assumed to be a smooth function. So if it doesn't vanish, we can just put that essentially on this side. We divide by that, and we put the x to the k on this side. So of course there's some steps which I show that everything is uniform and so on, but one can do that, and then essentially one arrives at this expression. Okay, so the kth order difference divided by this kth derivative at the point dk, that converges to x to the k as we make the h tend to 0. And the thing now is, okay, so what does this help us now. The thing is that this object on the left side here, this one you can realize with a shallow network. Okay, so because let's go back, right? So this is just the activation function, and these omega j's, they are taken to be h, and then you have here t, and then for the second part here, the omega is taken to be 0. So actually what you can show is you need, in order to generate that the kth order difference, you need m to be k plus, m has to be k plus 1. Okay, so that means this one you can realize by a shallow network with k plus 1 units. And that means somehow with these shallow networks, if you make the h small, you can arbitrarily well approximate the polynomial x to the k. And you can do that for all k's. Okay, so that means somehow if you look in the closure of the space, you can approximate in subnorm actually all polynomials. And if you know that you can generate the polynomials, then the last step in the proof is just the Weierstrass approximation theorem, which tells you that the polynomials they are dense in the space of continuous functions with respect to the subnorm on compactor, and therefore somehow the result follows then. Okay, so you see the whole thing is a reduction to polynomials, and if you have done that, it's done. But there are some interesting comments that we learn by studying the proof. So first of all, it's a constructive way to do that. Basically, we can now really, we have a formula which tells us what the weights are. And another thing, and this is I think a very crucial bit, is that the proof requires that these network parameters, some of them have to be taken extremely large and some of them have to be taken extremely small, right? So that comes because we have to make the h, right? So we have to let the h tend to 0, and the h determines the network parameters. So we have x times h here, right? So the h is then taking the role of the w, and we have to divide by h, which means it makes those coefficients extremely large. And so the whole argument is somehow, so you have to go to large and small coefficients. And if you remember what I was talking about last time in the first lecture, is about the initialization for the deep networks. We have this understanding that you initialize the network, and then you just change all these parameters a little bit, and that gives you a good solution. And that is not reflected here somehow. You have to change the parameters by a huge amount, which in practice is probably would give you something very unstable. But it is what it is. And another important thing is that for the argument, you don't really need a global activation function. Okay, so you just need, if you look into this proof, you just need a 1 tk where the kth derivative doesn't vanish, and that's all what you need from the activation function. Okay, it doesn't matter how the function looks outside this point, and that has the effect that you somehow that if you change the activation function on a very tiny bit, you can completely change the properties of the function spaces that you can generate. Okay, so suppose you take a polynomial, and we know for polynomial the activation, the universal approximation theorem does not hold because the space is much smaller. But now, instead of x squared activation, you make x squared, and you make a tiny perturbation of that, then immediately you get the universal approximation theorem holds afterwards. Okay, although it's just a tiny activation change in the activation function, but that changes completely the structure of the function space that you can generalize. Therefore, all these arguments which you see sometimes that you'd say, well, okay, here's the value, but now I take the smoothed value instead, and they look very close, so they should have the same properties. That's not necessarily true, and that's something which we learn also from this proof. It's really the local properties, they can matter a lot of the activation function. Moreover, yeah, so you really see that in the proof we really zoom in at one point of the activation function. And so now you can wonder, okay, so the assumption was that the activation function is arbitrarily often differentiable, and of course that doesn't hold for the value activation function, which we are now interested in. And you can wonder, is that now also true for value activation function? And you can extend that also to continuous function, the arguments. It's just a bit more complicated. So what you need to do in the first step is essentially you integrate the activation function with respect to a kernel, and that makes it a smooth function. That's something you can also realize by a shallow network. And then somehow the very general universal approximation theorem is to say it holds if the activation function is continuous and is not a polynomial. Okay, so that's the one of the most general versions that exist. But there are also versions that exist for bounded and non-continuous activation functions. Okay, so here I want to give you another idea about the universal approximation property if we go to multiple dimensions. Okay, so before we have been talking about this reduction step in one dimension, and here's another idea how you can work it out for arbitrary dimension. And this is in L2. Okay, so before the classical universal approximation property is stated for continuous functions with respect to the L infinity norm. And here I just do that for L2 norm, which for statisticians is somehow maybe even a more natural thing to do here. And so how does that work? So what is the claim actually? So the claim is that for any function in L2 on the 1 to the d, we can express it as a shallow network with m taken to be infinity. And then we have here coefficients. And so this means somehow the activation function here is the cosine activation function. It's one specific case, but this is particularly easy to show. And I can give you the proof on one slide, and therefore that's nice. So what you have to know is somehow if you have a orthonormal basis for L201, say the cosine basis, then you can generate an orthonormal basis for L201 to the d by tensorization of the basis. Okay. And so suppose we take the cosine basis, and now we expand L2 function with respect to this cosine basis. Then, if we write it out, it has this form. Okay, so that just follows from the classical L2 theory. And now what we do is just we use the addition theorem a lot of times in order to get rid of these products and to convert the products into sums. And if we have done that sufficiently often, then we will arrive essentially here at the sum of this type. Okay, and so you see in this case how you generate and where these shallow functions come from for this specific activation function. Now I want to discuss these other approaches, right? Which are based on rich functions, because we have shown already to activate the universal approximation theorem in one dimensions. Now what we can study essentially is how big is the space of rich functions. And there are different approaches, as I mentioned, and the first one is based on the Fourier transform, and it gives us some insight about how these rich functions, what they can approximate well. So just a reminder what the Fourier transform is, and the inverse Fourier transform, and you probably know that if you compose them, you get the identity. Another thing, what you can do is for complex number, you can somehow decompose it into the absolute value and the phase, and then you have a representation of this form. And so you can write the Fourier transform as the absolute value times the phase. And now if you use the inverse Fourier transform here, you use this formula and you stick that in, then you substitute this thing into here, and you get that, and then because you know it's a real valued function, so you can take the real part, and you can then take it inside the integral, and that gives you just the cosine here of the exponent. Okay, so what does this representation tell you? It tells you, well, every function in L2 you can write in this form, and this has really the structure now of such a shallow network. It's just instead of the sum, we have replaced this essentially by an integral. Okay, so this is an integral where here's a sum. So if we can make a Riemann approximation of this integral, then we arrive at a shallow network. Okay, and that shows you somehow that the every L2 function here, again, for instance, can be well approximated, where we have to be a bit careful with the Riemann sum here. And this is an idea. This has been used originally for the universal approximation theorem, but you can see easily that you also can get rates of convergence here for the because the universal approximation theorem is just somehow it converges, but doesn't tell you anything about the speed. But here you can also get convergence rates if you're careful with the Riemann sum approximation. And actually, this is what we later will see what appears in these approximation rates, which then lead to statistical estimation bounds. Another approach with using Fourier transform. So here, okay, sorry. Here's again the problem with this is that this is essentially a shallow network with cosine activation, and then once you have done that, you have to go from cosine activation. You have to go to other activation functions, or you can use ridge functions. It depends what you want to do. But if you want to go directly to any activation function, you can use this representation, which leaves you here the possibility to take any phi. It doesn't need to be the cosine, but the phi has to be in L1, and the Fourier transform of phi at 1 has to be something different than 0. It should be 0 here, so it's a typo, so such that you can divide through this number. Okay, and this is, you can easily check this identity because you just take again the Fourier inversion formula, and then you use this identity, which is just a substitution. So if you substitute here u, say, then you get the e to the w I to the e to the I w t x. You get it out, and then you get the Fourier transform. So it's very easy to check. And then if you have this formula and you just substitute it here, this part, you substitute that in this formula, you get exactly this. And that has really the structure of this sigmoidal. It has the structure of these shallow networks, and just the thing is the discretization. And there's another issue with this formula because the phi here has to be in L1, and then many of these activation functions that we consider, they are not in L1. For instance, the value function is not in L1. These sigmoidal functions, they're not in L1. But then what you can do is essentially you can always instead of this, you can subtract. You take the activation function at a point and you subtract it by a delay, and that gives you essentially then you can go from shallow networks with sigma to the shallow networks where you take essentially as activation function this one, and for sigmoidal activation functions which look like this, right? If you do this operation, you get something which is then in L1, and then you can do the formula from the previous page. If you have the value activation function, which looks like this, and now you want to make somehow an L1 activation function out of it, what you should do is you should just take the second order difference here, and then you get something which looks like this. Okay, if you compute that, what this means, it gives you this function, and this is of course an L1 function, and then with this function you can use the representation formula from the previous page. And you also learn a bit now from this formula again. So for which functions do we have good approximation rates? Those are functions where the Fourier transform decays fast. And that is very much aligned with the traditional non-parametric theory, where we always express smoothness in terms of Fourier decay, and then we get approximation rates and statistical bounds from that. Okay, maybe I should check the time. Perfect. Yeah. Another idea is based on the Radon transform. It's a bit related to the previous approach. So what you can do is, for the Radon transform, which just maps a function to all the line integrals, you also have an similar as for the Fourier transform, you also have an inversion formula. And so that gives you a representation of a function as an integral over a kernel, which then this kernel also depends on f, and I haven't written it down because it involves lots of function and operators like the Hilbert transform and so on. But all what you need to see here is essentially that you get a representation of a function of in terms of an integral, where the kernel also looks a bit like these functions that you have in these shallow networks. Okay, so that helps you, and that's a way how you can also prove the universal approximation theorem. By, again, you just have to essentially to replace this integral by a Riemann sum, and then you have to show that this converges, and that has been done already in the late 80s. Okay, so okay, so this was about the universal approximation property, mainly done in the late 80s and early 90s. And so the next thing is towards a better understanding is, what about approximation rates? And I was pointing to that already a couple of times. And here I want to mention three approaches. The first one is for smooth activation functions. The second one is an approach which relates to multivariate polynomials, again a bit like what we have seen before. And then the last one is the work by Andrew Barron, which is a function class which really somehow is and seems to be very naturally linked to these shallow networks. Okay, so the result for, if you have smooth activation functions, that's a result that goes back to the Hubikash-Maskar. And what he shows is that if you have a beta smooth function, say in Sobolev L2 beta Sobolev function, then the rate of convergence is that you need here to take the m, or if you have m units, you can get approximation error m to the minus beta over d, and d is the input dimension. Okay, so that's the classical approximation rate that you get of beta smooth functions. And so therefore that means essentially that these shallow networks, if you have a smooth activation function, then you get the classical approximation rates. And how does the proof work? The proof, again, it goes via first approximating polynomials and then somehow taking rich functions based on polynomials in order to, and then based on that you have essentially standard approximation theoretic results that tell you that this is the approximation order that you can expect. Yeah.
Maybe just a suggestion. I'm not sure that all of us know the rate of approximation, so you probably want to explain it a little bit.
Yeah. Okay, so now we have a function f, which is beta smooth, and it's so you can think about this as beta times differentiable, and think about beta to be an integer if you like. And then we have now a shallow network. Okay, so I shouldn't have also called that f. Okay, say the shallow network is G, and then we take a shallow network of this type. I'm sorry. And this result tells you then that this is bounded by a constant times m to the minus beta over d. And you see that if you make the M large, if you include more and more terms, we saw, right, this is a nested function space, so you make this function class larger. And that means somehow, this means somehow.
Is it beta over G or G over beta?
I'm always confused. So
It should
if
be
the
G over beta.
it's
The dimension.
exactly, yeah, you're right. Yeah, so the dimension makes it works. The smoothness makes it better. So that's the way I always remember it. But nevertheless, I'm very confused.
No, but it was in the denominator. I mean, it's 1 over n.
It's one. It's one. Okay, so okay, now we have to check what that means. So
Function
Making
beta
beta larger makes it better.
if d becomes very large, this becomes 0, so that becomes small, right? Yeah, so that's good. So and if beta becomes large, that becomes fast. Yeah. Okay. But everyone is confused about that. But you can always remember if you have a smoother function, you get better rates, or you should get better rates. If you have more dimensions, the curse of dimensionality, you get slower rates if you have additional dimensions. Okay, does that help? Maybe, yeah.
And these results holds for any smooth estimation function.
So the function, this result only works if you have some, and smooth here I mean really with C infinity, so infinitely often differentiable activation function. So not for the value activation function. So that's of course the limitation of this result. Another interesting result is that, and that relates to your point. So there's a work by Petrushev, and it shows that even now you could think, right? So suppose I take here an activation function which is Lipschitz like the value function or so. Okay, so then you can maybe think, well, then I can maybe only approximate well functions that are also at most Lipschitz, right? And afterwards, if it's more than Lipschitz, you get some sort of saturation because the approximating function class is not smooth enough. We often see that for function systems, but here it's not entirely the case. So what he says, or what he found, is that if the activation function is as smooth, okay, so again in the Sobolev sense, you can get the optimal approximation rates, which are those ones here, for functions up to smoothness s plus d minus 1 over 2. So there's an unexpected thing that if you have additional dimensions, you can also approximate smoother functions with a non-smooth object. And this is really a dimension effect. So if you have d equals 1, in one dimension, you know in one dimension it's not true. And then if you have larger dimensions, you gain here something. And I don't want to go through the proof because we don't have the time. I just want to show you what the proof techniques is. This is really what was explained before. So first step is you reduce to rich functions by doing the universal approximation theorem in one dimension and getting a rate for that. And then you're at rich functions. And then you use this approach via the Radon inversion. The Radon transform, you know that has a polynomial eigenbasis. And then you again use essentially just multivariate polynomials in order to approximate functions. And for that you can use standard results about approximation rates. And it's a more or less constructive proof. And that has also many more consequences that I didn't state here about how you should choose these parameters. It tells you a bit about where to look for these WJs and so on. Okay, so why is that true? Why is that true? So the thing is that you see, so you need the activation function. If you think back about this reduction to rich function, you just need it for a one-dimensional problem. But the whole thing is a d-dimensional problem. So even if you don't approximate well in one dimension, it doesn't matter because the underlying problem is more difficult. So therefore you have a bit of room to play, and that is exactly what explains here this effect that you can, in higher dimensions, you can approximate even smoother functions. And it's interesting to see that shallow networks have this property. Right. Okay, so what you can criticize about all these proofs is that they always first go to polynomials. Okay, and then they use essentially polynomials in order to get the approximation rate. So you could then say, well, we could have started instead of shallow networks, we could have started directly with polynomials because it's just a great thing. Why should we do an extra step and do these activation functions? And based on these proofs that I presented to you, there's nothing you can say against this thing that you could just do polynomials directly. The only thing that comes now is the Barron's result, and this is a result where there's a, it's not, the proof is not done via approximation by polynomials. Okay, so the proof is based on an abstract thing which is called Maury's theorem. It's credited to Maury, but appears in a paper by Pézier in the early 80s already. And it says something about so if you have a subset of a Hilbert space, and so suppose that you have a function that lies in the closure of this subset of the convex hull of the subset, then you can find functions g1 to gm such that you get an approximation rate of 1 over square root of m, and here you have to take a constant that scales with the sup over this space. And it's so it also has a very nice proof. It's actually, you can prove it by probabilistic argument. You show you define a random variable, and then you show that the expectation of this random variable is bounded by this quantity, and then you know if the expectation is bounded, then there must be a realization of this random variable for which this is also bounded, and that gives you this result. Now the rate 1 over square root of m has been shown it's not the optimal rate. You can even get a slightly faster rate here, but Barron uses this rate, and I would just recall these results. But you can actually get slightly faster rates if you would invoke this improvements by Markowitz. And that can be used to derive shallow networks, because essentially what it does, it does the Riemann approximation step for you, right? So you can define that to be the integral, and then you know somehow within this integral you can find such a sum which approximates then with rate 1 over square root of m. Okay, so this is what Barron did, and he uses the Fourier representation that I have shown you before, but there's a slight trick here. What I have shown you before is just the formula for f of x, and then you wouldn't have the second term here, right? So that's just that we did. And he also subtracts this f of 0, and that makes this function scale with the L1 norm of w. Okay, so because it's a Lipschitz function, somehow then these things they cancel out, and you don't have good control on them, and then the whole thing scales with w. So that means somehow you can divide here by the L1 norm of w, and you can multiply here with the L1 norm of w. So if you define that, so you can write the whole thing, you can write it like this, where you define lambda, you just normalize that. Okay, so you do this trick with multiplying and dividing by the L1 norm of w, and then you normalize that with this constant, which makes this a probability measure. And you will see in Barron's result, this is the function space later. Okay, so it comes from this representation. So and that defines what the function space is. This constant. Okay, so you make this a probability measure, and then you have these functions which are bounded. You can see that because of the Lipschitz property. And so we have something which is of this form, right? So we know, that the f lies in the convex hull of something, because so this is a probability measure that defines somehow the convex hull of all functions of this form, and that generates the f. Okay, so that means somehow we can within this space we can now then with this Maury's theorem we can select m representative elements such that we get rate of convergence 1 over square root of m. And that's the whole argument. There's one additional step, is that again here, what I explained before, this is just for the cosine activation function. So when you want to generalize it to arbitrary activation functions. So this is the step which maybe I don't explain really here, that you can embed this the convex hull of this space into the convex hull of that space. If you take here and here, you can take any sigmoidal activation functions. Those are activation functions that look like that. Okay. So the whole thing is just to write the function f now as an element of a convex in the closure of the convex hull by making this a probability measure. And then if you apply Morris theorem, what you get is it's just a straightforward application. You get that you can write this function by a shallow network with m terms, and you have the f0, right? It was in the representation. You can take that also as one unit, as a constant, right? So you would have essentially here m plus 1 terms, and you get the rate 1 over square root of m, which is the rate from Morris theorem. And here is the CF again, right? So we have to, if you go back, you have to put here the soup over this function space. So if you, yeah, so it's an easy computation somehow to see that this scales then with the CF, and the CF is of course something which can also be infinite for some functions. So that defines your function space. What is interesting now, if you think back about our exercise from before here, normally these approximation rates that we get, they scale somehow in something like a 1 over d or minus beta over d or so. You don't see any d here. It's a well, there's something in the constant, of course, depending on d and this constant, but the rate in m is just a 1 over square root of m, so it's not depending on the dimension, so it's dimension free. And then people have been wondering whether you can hear whether this is an instance where you're better than the curse of dimensionality, or so, because you don't have this d in here. That's the interesting observation, I think. Okay, so let me comment a bit on the rate. So we call what this CF is. And so it looks like as if, and many people have claimed that this is something very special which only neural networks can do. But there's actually an argument by Emmanuel Candes which shows that these, if you make a good Fourier series where you truncate the small coefficients and also keep the first coefficients, then you can even achieve a faster rate for this. So here you have the rate 1 over square root of m, and for this Fourier series you can even get a rate where you take m Fourier coefficients, you can even get a rate which is slightly faster, because it also has this additional term here, minus 1 over d. And this is, I think, if you would get the better Morris theorem with the faster rate, you would also get that. So in the sense they match. And there's nothing in this approximation theorem, there's nothing special about shallow networks here. Okay, so I think it's fair to claim that all these approximation theoretic properties that have been established for shallow networks, that they can also be established by other methods, either polynomial methods, that's what we have seen before, or you take Fourier series methods. And so there's no magic in the shallow network here, because it's not it's not much. If you compare it to Fourier series, you just have the possibility instead of only choosing the CJs, you also can choose the modes essentially, or the something inside this function system. But this doesn't add too much to the overall function class. So there's not much you can gain here. Okay, so I have 2 more topics, and I have to see how I do with the time. Okay, I have 10 more minutes basically. So the first one is how do we fit a shallow network to data? So if you do the gradient descent, you have the problem that this energy landscape in principle can have many local minima, and you can get stuck in that. On the other hand, what you can do is you can try to define the global minimum, which is the empirical risk minimizer. But then you have somehow to search over all these parameters. So it's m times d plus 2 actually. So there should be 2. And then the question is, well, can you devise an algorithm which has at least a theoretical guarantee? And people have been thinking about this. And so this is a greedy algorithm. And what you just do is you initialize with the zero network. And in every step, you take your network that you have built up to that moment. Okay. Suppose so you pick a loss function capital L, say L2 squared error loss or whatever you like, and then you take the network that you have built in the previous step, you scale it, and you add one more unit to that, and now you look for the best fit over all these 3 parameters here. So you keep the previous network fixed, but you scale that, the gamma and all these from this additional unit, which minimizes that. And that is then how you define your shallow network in the jth step. Okay, so it's iteratively in every step you add one unit and you balance the previous one with one parameter. And that's something you can theoretically analyze. So first of all, instead of, right, so before we said the empirical risk minimizer would have to search over m times d plus 2 parameters over the whole parameter set. And here, if you do this greedy algorithm, in every step you search over d plus 2, maybe I'm wrong, maybe it's d plus 3 because you also have the alpha here. I think it's d plus 3 parameters. Okay, so but you see it breaks it a bit down, but still if the d is large, it's still a very hard problem. And for this algorithm, what you can show, it has the rate 1 over square root of m, and this is also a bit the same rate that we have seen that occurs in this theorem by Maury. So it has a theoretical guarantee and it's quite fast in terms of the m, but people in practice they have abandoned it because apparently it has not a good. I've never tried it myself, but that's what I know is that it's very hard. It cannot really look ahead, and therefore adds many stupid units to it, such that it doesn't really perform well in practice. And I think this might be an issue with whatever we do. If we want to do the statistical theory for deep networks later, we could in principle also imagine to define some algorithms on our own where we can really make proofs for them. But although they might have good theoretical guarantees, that might not really help anything to build better practical algorithms. Okay, so finally what I want to do, the last 3 slides of my talk, I want just to show how this can be now extended towards statistical guarantees. And for that, if you do statistics, you need to say something about the data. You have to impose a statistical model on the data. So in here you just do regression, and so that's follow here the work by Baron 94. So just say the responses are bounded, and that the thing that you want to estimate or learn from the data is the regression function, which is just a conditional expectation of the outcomes given the explanatory variables being x. And that in particular covers the binary classification. So if you have yi to be 0, 1, then you can see this is the conditional probability here. And so here's what Baron did is he used this empirical, or he studied this empirical risk minimizer, which is now the argument over all parameters in the shallow network. And then by standard exponential inequalities, the simplest one that you can imagine is that you take theta to be a discrete set. Okay, so you don't allow any parameter, you just allow the parameters to lie in a discrete set, which with finite number of points, and then you can show that the expectation and the risk, the statistical risk or the expectation of the loss is bounded by the squared approximation error plus the term that accounts for the statistical variability, and this term scales like log the cardinality divided by n. Okay, so then if we have been talking a lot about the approximation theorem or approximation properties, so that you can stick in here, and then the variance part, you just have to count essentially how many parameters do you have in your space. And if you have to discretize, then you get here in trade-off, because if you make that if you have too few parameters left, then you get bad approximation rates. If you make them too dense, you get large variance. Okay, so this is the thing. what Baron then worked out. What you have is you have m times d parameters of the order m times d parameters, right, in the shallow network. And what you can show is that if you make a discretization in every parameter of, say, order 1 over n over a range that extends to infinity with a polynomial n, you get that the cardinality is the product, and then if you take the log, you get somehow the number of parameters times log n as the thing which we have then to stick. And here I take d to be fixed, and then if we use this formula from before, we have to stick in this upper bound for the log of the cardinality, and then we get here an m log n divided by n, and the 1 over m, that comes from the approximation rate, right? So it was 1 over square root of m, but now we have to take the squared loss, so we get a 1 over m here. And that only holds, right? The whole result only holds and for functions for which this constant is finite. That is a weird function space. It's not so clear how to relate that to classical smoothness spaces. And then what you can do is you can now wonder, so how should I pick m, right? How many units should I put in my hidden layer? And then, of course, a good choice is based on this bound to take one which balances these two terms. If you do that, you get this m, you have to choose it of this order, and then you get, if you stick that into this formula, you get a rate of convergence is square root of log n over n. Okay, so that tells you a bit what is the critical thing in the shallow network that you have to arrange is, or that you have to choose is the number of units. If you have too many units, you make the variability too large. If you have too few units, the approximation property is not done well. Okay, so the crucial hyperparameter is really the choice of the number of units in the hidden layer of the shallow network. That is the one you have to have on the right order if you want to have good performance of your shallow network. Okay, so this is just a summary of what I have been talking about today. So we started with the universal approximation theorem, which just says somehow that functions can be approximated but doesn't say anything about the rates. And then I mentioned some result about rates of approximation, and finally we discussed these estimation risk bounds. But there's also, it looks like, right, again, it looks like as if you have here something which avoids the curse of dimensionality because it doesn't depend on d, which we normally have in a d-dimensional problem in non-parametric statistics. But there's nothing special in here. So that's really what I want to claim. So you can achieve the same rates with other classical estimation strategies. Okay, so and what I want to do next week onwards, I want to talk about what does it help you to have additional layers in your network. Okay, so which functions, where do you get particularly good approximations, and what is so peculiar or so special about these additional layers? And that is what we want to do on Wednesday. Yeah, thank you. Mm-hmm.
We probably have only time for one quick question. Okay, well,
Yeah.
now I'll
Okay.
see you
On
next
Wednesday.
Wednesday.
Yeah.
Thanks. Let's thank the speaker.
Oh, yeah.